Hello everyone, this is week 10. This week we will be talking about the frequency domain methods. Up to this point, 9 weeks, we have talked about time domain design. We have talked about the poles and zeros, zeta and omega n lines, what they mean, and then we've talked about the dominant pole placement. We have designed certain controllers, PID controllers, PI controllers. We also have talked about delay and dead time. Now at this point, we will change our perspective. We will be looking from a frequency domain point of view. This means that we'll kind of repeat the time domain design in frequency domain. Now, I have talked about the frequency domain. I've talked about the body plot, which is mostly used in the frequency domain. Now, let's look at our task today. We will be using the body plot throughout this course today. Now we have a third order system. We have a transfer function. And we will look at the controller, p-type controller stability. We will look at the p-type controller design. We will look at some lag controller design, phase lag controller design. We will also look at systems with delays, which I've told about you in the previous lesson. I've talked about the fact that we can also use frequency domain for delay time analysis and also maybe synthesis. So let's get going. Let's look at the p-controller stability interval. But before that, let's take the system and let's look at the body plot. Now, usually what you can do is you can just use the body function here. And with this body function, you can just provide a transfer function to it. Once you run this, let's run it. It will generate you the body plot. Now, at this point, you can also use the graphical user interface. You can use this figure here and these tools here, and maybe right click here and look at the properties, characteristics, etc. But I'm going to take a different route. As it was the case for the root locus, I'm going to calculate stuff or use the body function and calculate stuff using that. So let me show you how to do that. We can use the body plot function here, but as it is the case for the step function, I can just request the function to return me the magnitude, the phase, and the frequency here. But I have an extra step here, because once we have this, let me again run it. Now, once we run this, you'll see that nothing is generated, the figure is gone. But you have something called magnitude, something called phase, and you have also omega. Now, omega makes sense. I can see that omega is a vector, and it ends at 1, but it's logarithmic, and it's 10 to the power of 3, etc. But for magnitude and phase, we have an interesting structure here. And namely, we have not only 2 dimensions, we have kind of 3 dimensions here. And the reason for that is the following. Throughout this course, we always use single input, single output systems, transfer functions. We have a Laplace domain transfer function. It has just 1 input and 1 output. Sometimes we might also look at disturbance and noise, but they are not inputs that we can manipulate for control. So they are not control inputs. So therefore, if we look at a transfer function, it's mostly single input, single output systems. And it doesn't have to be a SISO system. If you call the body plot and look for magnitude and phase plots, you can have multiple channels, input channels and output channels. And from each input to each output, you will get a gain and phase change. Therefore, you will get plots. But in our case, that's not the case. So we need to get rid of the extra dimensions, because this is just a 1 by 1 by, I don't know, is it 69? So We can check that by looking for the size here, and you'll see it is 1 by 1 by 69. But yeah, we have only one dimension here and here, therefore we don't really need that. What you can do is you can use this operator here, parentheses column. It will convert it to a 1D array. This is actually just accessing by 1D. You can do this for all types of arrays, n-dimensional arrays or matrices. But we can also use a command that is more self-explanatory, namely squeeze. So the squeeze will just get rid of the unnecessary dimensions, and I'll use it a lot because it's explaining itself very well. So therefore, let's use that. Yeah, let's have the face and the face here. So this is quite helpful, these 3 lines of code, and the reason for that is the following. If I run it, you can see now I have mag, and I look for the magnitude, basically the size of magnitude, the face, and also omega, and you can see that they have the same size. And I can then generate my plot, so I can go ahead and create a figure. You'll argue why I am using this instead of just using the default. Well, you'll see in a moment, but it is easier and visually more helpful to use this in the laboratory sessions. Let me also take the handle here. So I know that X label for each will be omega, and Y label is always the gain. So let's maybe write it down like this. But here we will have the argument, the face, and again omega, but this is the second axis, and we'll have the second plot. Now, once I've done that, what I can do is I can go ahead and plot it. Omega mag, line width maybe. Now this will be the first axis, this will be the second will be the magnitude, or the face, of course. So there we go. Now this will look a little bit different, and you'll see why. Let's call this script. Now this doesn't seem to be a body plot, but in fact it is. There are 2 basic differences. One of them is that we don't have any decimal in here. The second being that the x-axis is not spaced logarithmically. We can change that by just using the set function, GCA, and then x scale, because we want to change the x scale of the axis. It is not changed by default to logarithmic. So if we do that, we'll see that we have kind of a body plot. Now the main difference here is that we need to use 20 log and then mag. We can do that and you will get decibels, but I'm going to skip that because I'm going to focus on controller design and analysis. Therefore, seeing the gain value will help me out. Now, of course, this seems to be a little bit of work, but once you have coded this part, you can just copy and paste it, basically. So it's not really that big of a deal. Now, again, this doesn't seem that much, but from now on, I have the magnitude and phase vectors calculated. And the way that we will be working is the following. We will have always a certain thing that we're searching on the body plot, because we will use the body plot itself. Therefore, having the vectors, having the values in a vector is quite helpful. You might look for a certain phase value, you'll search through the phase vector, and I'm going to show in a minute how to do that. Or you might look for a certain magnitude value and the frequency where that happens. then again you have the vector, so you can do that. And I can also automatically generate stuff. We'll see. Now, we have this body plot, and this body plot tells me stuff about the transfer function, about its behavior. I can, for example, see that for certain frequency variable values, in this case low frequency values, we have a certain gain. And then, after the crossover frequency, if it's a filter, we have basically zero gain. Now, the gain here, by the way, is really, really small. So if we want to look for a controller like the p-type controller, we will most probably have huge values because, well, the gain is really low here. This is not maybe the perfect example here, but most of the time you will see 1 here as a gain. That means that we will just have gain 1 for these frequencies. So for low frequencies, we will have gain 1, which would then correspond to a reference tracking, for example, because from input to output, we have gain 1, which means that the output is the input. If it's a closed loop, this will make sense. Of course, this is an open loop, and if I apply step to it, I will see that there will be a low gain. And you can check it out. You can just look for this. Look for the step response. Maybe we should also create a figure. The step response of GS. And you can immediately see that the gain value here matches the body value. There we go. And the step response is a low frequency signal, basically. It has some high frequency values, but we could consider omega equals 0 almost the step response here. Yeah. So, again, this is not really that important. What important is the following. Now, we were using the transfer functions in the time domain analysis and synthesis to come up with polynomials and poles and zeros. All that stuff is not the concern in frequency domain. In frequency domain, we're not really interested in poles and zeros. We will use them indirectly, but we are not directly interested in them. Now, if we have a certain transfer function that is depending on GS, and for example, if we have a K value here, the p-type controller, FSS or FS, then we can look for the closed loop here. This is already what we do, K times GS, and then 1 plus K times GS. Now we all know that this closed loop transfer function will depend on, it's a function of S and K. So if I know the K value, for example, if K is equal to 1, then this will be an expression that's depending on S. And the frequency domain, or for our frequency domain methods, or during the body plot, what we do is we do S equals J omega. If you remember this, we talked about this. We substituted GS and then S equals 1i times omega. And if we do this to a transfer function, we'll get a fraction, and that fraction will depend on omega, and it will be a complex value. If we change omega, as it is the x-axis here, let me again generate that. So if we plug in a certain omega value, we'll get something like a plus 1i times b. And in polar coordinates, we can convert that into a gain and phase. So therefore, we have this data here, where we have gain and phase versus omega. And for that, we're actually using a fraction, or the transfer function. So, and if I plug in j omega, I can use that. So what I'm basically trying to say is the following. If we have GS, we can use S equals j omega and convert it into g omega. If we have K, since this is static, it will still be K. If we have FSS or FS, it will be converted into F omega. And the conversion is done via this one here, s equals j omega. And that's it basically. Everything depends on this fact that we plug in s equals j omega, and it will be frequency dependent, therefore we are using frequency domain methods. How can we do that? Or a better question is, how can we calculate the stability interval for p-type controllers for a given transfer function? Now the case here, and even if it's depending on, let's say ts, the closed-loop transfer function, is now t omega. Means that it is depending on omega, it is a complex valued function, and that's it. Now if we have an input t omega and output, so like this, and I have just a function t omega, how can I look for stability, or what does instability or stability even mean? Now keep in mind that we will have something like this, ns plus divided by, or k times ns divided by ds times s plus k times ns, something like this. So what is this? This is basically ns divided by ds is the open loop transfer function, and we for some reason have or maybe let's get rid of s, we have a p-type controller. This would be the closed loop transfer function. And if I plug in s equals omega, I'll get n omega d omega, and I'll get this fraction here, which is basically this here, but s equals j omega. Now let's consider 1 divided by s, which is an integrator. If we have ts for some reason equals 1 divided by s. Now this is not a stable transfer function, therefore we might look for this. Now yeah, if we have 1 divided by s, and if we apply a constant, then we can see that it will give us a ramp output, a ramp response. And if I'm giving a constant as an input, that would mean that it is basically a zero frequency input or low frequency input. And yeah, you can see that this is basically 1 divided by j omega. And for low frequency or zero frequency, I'll plug in 0. And this would give me 1 divided by 0 plus j0 or 0. Therefore, if we look at the limit, we'll get infinity. So yeah, hope that you got the idea. It is basically division by 0. We are looking for division by 0. And that's it. We have a certain fraction, and the only way that we can generate a infinity gain that corresponds to unstable output would be to get a division by 0. So therefore, for any stability analysis, we will try to look for the denominator and we will try to equate it to 0. Now this is nothing new. We actually know this because we're looking for the characteristic polynomial. We plug in s equals j omega, we take the real part equated to 0, imaginary part equated to 0, and that corresponds to instability. Therefore, what we can do is we can use that fact. But there's also another way, which I'm trying to show you, because if we have a body plot, why not use it? Now, in order to have, let me just change gs into omega here. So this would be t omega, and then we have f omega, etc. Since we want to have 1 divided by 0 or division by 0, what we should do is we should look for the denominator of this. We should look for the denominator, and that should be equal to 0. So we will be looking for this equation. Now in this equation, g omega is a complex number that has a certain gain and a certain phase value. But our controller is basically a static controller. So if we use this equation, we can see that this will become immediately -1. If this part is equal to -1, then we will get a division by 0. Now, there's also the fact that -1 is in Cartesian coordinates, and our body plot, or g omega, will be in polar coordinates. So change of coordinates would result in the following. This would be gain 1, but argument, let's have this, minus or plus 180. So you can use cosine of minus 180 plus I times sine minus 180 times 1, basically. So yeah, this gives us an idea about stability, and actually we have two equations here. One of them is k times g omega should be equal to 1. This is the gain condition. And then argument g omega should be equal to minus 180 degrees. K times, actually. There we go. Now this is basically the same. We have this equation and we will be looking for this. Now if we have k positive, let's assume that we have k positive. Examining this would show us that instead of using this, we can just take this out. Because k is positive. Now at this point, we can also look at the angle condition here. And if we have a multiplication, the sum of the arguments is basically the argument of the multiplication. So instead of having k times g omega, the argument of that, we will have arc k plus arc g omega. And since k is a positive value, it will have a 0 degrees phase. So I can get rid of rk, and we're left with that. Now let me get rid of the additional steps here. So we basically concluded that we need a division by 0, and that would happen by equating the denominator to 0, and that gave us that the multiplication k times g omega should be -1, and we've changed that from Cartesian to polar coordinates, and we've then decomposed it into the gain and phase conditions. And then we've assumed that k is positive, therefore we have k times g omega should be equal to 1 in terms of gain, and argument g omega, because k has no argument, should be equal to minus 180 degrees. So what does this mean? Well, if we are using the body plot, let me also bring it to the front. If we are using the body plot, we need to find the point where the argument is equal to minus 180 degrees. And you can check the second figure here, second plot here, and you can see that at some point, somewhere around here, we have minus 180 degrees. Somewhere around here. But yeah, what does this help with? Because if we are looking for the argument, and if it's negative 180 degrees, what am I getting out of it? Well, actually we are getting the frequency, because for which omega is this satisfied, we need to find that, and then we will plug in that omega here in order to get k. Because if we take the symbolic approach, what we would do is we would plug in s equals j omega in here, and look, define k, and then look for the closed loop and get the expression there, and we would see that equating this to -1 like this, or this one to 1 and this one to minus 180 degrees, would result in two equations and two unknowns. One of them is k, one of them is omega, and these are the two equations. Therefore, there will be a solution. But since this is independent of k, this equation 2 does not depend on k, we can directly calculate omega. Once we have obtained omega, we can plug it in and calculate k. We don't have to solve them, we can just solve them individually. So they're not coupled, basically. Therefore, if you have a body plot, you can just directly check for the argument. Look for the point or the frequency where negative 180 degrees is, and at that same frequency, we can look for the gain, and that gain will tell us what the p-type controller should be in order to result in marginal stability. Well, basically, it will be the inverse, since the multiplication should be equal to 1. If this is 0.2, then this should be 5. So that's basically it. Now, let me demonstrate to you that. So, we are looking for the argument of g omega that should be 180 degrees. At which frequency? So, I'm going to obtain this numerically. You can also use the symbolic way, but I'm just going to stick with the numerical way because I can use the body plot. So let's actually take this phase vector here, take the difference between 180 degrees and this phase, take the absolute value and look for the minimum. So minimum of this. Well, we can look for the value or the index, but I'm more interested in the index because I'm going to find which element of this vector satisfies or has the minimum difference between 180 degrees and phase. You can also look with a for loop individually, you can just check each one out, but the problem here would be the following. I'm not directly equating this to 180 degrees because it might not be exactly equal to this. But I'm okay if it's close enough. So therefore, I'm taking the absolute difference between that, between the phase and minus 180 degrees. I'm going to look to minimize that. And if this is exactly equal to negative 180 degrees, you'll see that this will be equal to 0 because there's another negative sign. So this should give me, so let us check for omega val. This would be, we have omega, yep, index. So the same element, but in the frequency vector in omega, we are looking for the omega value. Also, what I can do is I can again check the phase angle. Phase val. And maybe gain val. So I'm basically obtaining everything based on argument equals negative 180 degrees. So we, oh, this is called mag, not gain. Mag. So magnitude value. So let's also display a nice message maybe. Let's say we have argument of g omega equals minus 180 degrees. At omega val, and maybe we should also display g omega star equals to mag val plus phase val. So let's also display an empty one. So there we go. We should maybe put it in space. Now there we go. We have this here and the data here. Now it tells us that minus 180 degrees is at maybe omega equals, so would be a good idea, omega star equals, so I'm sorry. So there we go. Now we can see that we have at 6.21 radians per second, we have negative 180 degrees, or the closest value to this. And you can see at that frequency we have gained 0.00249, and the angle condition is minus 184. Of course, we need to maybe increase the accuracy of this. And I know that the frequency is around 6. So what I can do is I can define the omega value. Up here, I could say that let's use log space. Let's use... that's actually enough. Let's use 400 points. So I have to find a logarithmic vector, and I'm going to provide this to Bodhi. It is basically the same as it is in the step function. You can provide your own time vector and then calculate the step response. Here you can provide your own frequency vector and calculate your Bodhi. So if I do this, because omega is like this, it might miss the exact value for 180 degrees, since it is logarithmic. You have 10 to the power of 3. So in order to get rid of that problem, we didn't got rid of that. Oh, not minus 1, 1, of course. So here you can see we have fixed that issue. The exact frequency is not 6 point something, it is 5.84. Now, at this point, if you use the symbolic method, if you're just going to calculate it by direct substitution, then you'll see that it is in fact a better and more accurate way of calculating that. But here I'm just using the Bodhi plot, and if you, for example, have a printout of this Bodhi plot, what you should do is you should just take your ruler and draw a line from here, minus 180 degrees, and then draw a vertical line and a horizontal line in order to check for the frequency here, and then you'll just draw the line here to match that frequency of both plots, and then again one horizontal and one vertical line, and you'll get the corresponding values here. So that's the old school method of obtaining this info from the Bodhi plot. So I'm basically emulating that for this. So now we have found the frequency, we have the gain. We have the gain of the system. The only thing that we should do is we should come up with a p-type controller that amplifies the system so that k times g omega is equal to 1. So in order to do that, I can just take the inverse, and it'll show me or give me the value that I'm after. So 1 divided by magval will give me the p-type controller. So let's add that to k star is kval, and that's it. By the way, we are not really that limited. Namely, what we can do is we can just go ahead and plot this on ax1, take omega val, take mag val, and maybe a square and line width 2. We can basically show this point on the figure. So let's have face val, and there we go. Not only that, I can also create feedback, use kval times gs, comma 1, and maybe look for the step response, the pole zero map. Let's only display the zpk of the system. So let's see. There we go. Of course, I have kind of changed the x-axis here. It stops at 10. Therefore, we are directly getting the point of interest. You can see by clicking here. And this was what I meant at the beginning. You can just directly click and find it, but I'm kind of showing you the numerical calculation or the old school calculation of this whole thing here. You can see that there's also a numerical sensitivity problem here. If you have a little deviation here, since we take the inverse of that, it will affect the value hugely. So keep that in mind, and we can see that it is almost 0, and if this is 0, s squared plus 34, the square root of 34, by the way, gives us again the frequency 5.83 or 5.84. It seems like this is what we are looking for. Again, we can see that this is not stable, but it is close to the j omega axis. If you think about the zeta value of this second order part here, you'll see that zeta is almost 0, so that's exactly the point that we are looking for. But again, if you want to solve this issue, if you want to be even more correct, let me find that, then you might also skip the log space. You can convert it into ln space. 0, 1, 0, 10, 400 points instead of logarithmically, you might get also that. And it kind of messes up the logarithmic plot because you have linear data and logarithmic plot, so they don't work really well. But you can see now we have almost 0. It's even better, and here you can see that. If you want to be safer, you can maybe take one previous index here. It's this element here. Maybe you can use 233. Let's see, phase 233. Spelling mistake. You can see that it is almost 180 degrees. This is maybe a safer value. So subtracting one could be a good idea, but yeah, it's just sufficient, I guess. So now we've seen that the upper value here is basically this value here, 351 approximately. But keep in mind, this is not the only thing that we can obtain from a body plot, because we did have an assumption that the k value should be positive, and therefore we looked at k times g omega, and we said that this should be 1 and minus 180 degrees. Now what if k is not positive, but it's negative? What then? Well, let's look for the gain. K times g omega equals 1 is one of the conditions. Now in this case, since k is negative, this would be minus k times g omega equals 1. And let's also use the argument of k times g omega should be equal to negative 180 degrees. And let's also use the fact that rk plus arc g omega would be the same thing here. But now, since k is negative, if it is positive, it will have 0 phase. If it is negative, and since we also use negative 1, you can directly see that this value should be negative 180 degrees. So therefore, we should be looking for argument 0 here. Let me get rid of the unnecessary stuff here. Now you can see that we will look for arguments g omega equals 0, and at that point we'll take that frequency and look for the gain value at that frequency, take the inverse and put a negative sign in front of it, because k would be then equal to minus 1 divided by g omega. And it makes sense that k is negative because we are looking for k negative values. So there we go. Now The only thing that will change is I'll just take this, and maybe this. It makes sense. Put it in here. Now, instead of having that, I'm just going to get rid of that. Of course, I know what which element this is, but just to be compatible. Now, phase value, mag value, the only difference here being that I should use a negative value here. And yeah, that's basically it. Let's pick another color. Let's have blue for some reason. And let's comment this out. Now here, of course, the message is not correct. We're looking for this. Now here we can see the arguments should be equal to 0 at omega equals 0. At that we have gained that, and this is 0, therefore k is minus 24. So of course we can also check the same thing here. We can just use this and plug it in here. K value is of course negative. This should work. Now it is interesting and important to note that since omega is equal to 0, we plug in s equals j omega, but j0, we are basically talking about the origin here. And you can also see that we have a pole at the origin for this exact value. And this is again not a stable closed loop, nor is this one. So we have the interval minus 24, 351, approximately. So you can see that we kind of can use this in order to analyze a system. And the nice thing is that we actually don't really require the actual transfer function. We don't need to know the poles, the zeros, the gain of the system. We don't need anything. The only requirement is that, or limitation is that, we need the body plot of the given system. Of course, and if we are looking for a p-type controller. So if we have the body plot, it's not really important where it came from, but it is important to have one. And if we have this body plot, we'll just search certain phase values in order to determine the stability. And for those phase values, we will look at the frequency. At that same frequency, we'll take the gain, take the inverse for the upper bound on the stability interval. And we'll do the same, but this time for zero phase, it will certainly most of the time appear at omega equals 0. Therefore, we'll take the gain value at that specific frequency and take the inverse and put a negative sign in front of it. And it'll give us the lower bound. So that's it, basically. So this is one thing. So this is analysis. And you can see now that every transfer function can be used in the same way. Plot the body plot. You look for minus 180 degrees and 0 degrees most of the time for phase value. Just look at the frequencies, the gain values, take the inverses. One is negative and the other one is positive, and you have the stability interval. What about a design? Let's think about design. Now here, I'm not going to open. Let's say this is basically design step. And we had analysis here. Somewhere here. There we go. So we have overshoot 10%. The thing here is that we don't really know what to do now. We just have a body plot and we have 10% overshoot. The most we can do for now is to calculate the zeta value, the corresponding zeta value, which is pi squared plus log overshoot squared, and that's it basically. So what can we do now? Now, yeah, here we will use something that is not maybe that obvious. Now, determining the interval, the stability interval, actually is the point where zeta is equal to 0, because we are on the j omega axis. But what we want to do is we want to come up with a way of determining which frequency we should use in order to get the corresponding overshoot value. Now, the only thing that we know is that if we go here somewhere or here somewhere, if we decrease the frequency, and this is the stability point here, then we will basically increase the zeta value. Why do we know that? Well, if you have a closed loop, if you increase the gain value, you'll see that at some point the system will have more and more overshoot, lesser and lesser zeta value, and at some point you will hit the marginal stability point and then you will be unstable. So therefore we can safely assume that somewhere here we will have a higher zeta value, maybe 0.1, 0.2, 0.3, 0.4, up to 1, and then it'll not matter that much. So, yeah, and we will have basically a formula that will help us here, which is not that pretty, because up to this point maybe you thought that this overshoot formula is bad. Now you will see worse. Now here what we will do is we will associate the distance to this marginal stability point to overshoot. So we will have a certain distance, we will go back a certain distance in frequency, and that will hopefully help us in determining zeta. By the difference or the distance, I mean, of course, the distance from minus 180 degrees. Now, we were looking for k times g omega, and the argument of this to 180 degrees. Now, we don't really want to have 180 degrees, because if we have this, then it's not stable, it's marginal stability. But we will change this by adding a certain amount, let's say 20 degrees for example, and we want to have a gain of 1 and degree of 160, and hopefully this will correspond to a certain zeta value, therefore a certain overshoot. Now we know that this point, minus 180 degrees, corresponds to zeta equals 0, therefore we have basically instability, and the overshoot is maybe, yeah, there's no overshoot because it's not stable. If it's a sinusoidal value, of course, this is basically 100% overshoot. But yeah, if it's not a sinusoidal, then there's no overshoot. It could be a integrator, therefore, yeah. But let's get rid of overshoot. Let's say instable, not stable, to be more correct. So, therefore, we need to associate this distance in the phase angle to a certain overshoot value. And therefore, we will have a formula, and I'm just going to write it down, and you will use it because I also just use it, because yeah, it is what it is. So the formula goes as follows. We have 2 times zeta, so basically you will use zeta, and this zeta value will help you in determining the distance, or the phase margin, which is the technical term. So minus 2 times zeta squared, and then plus another square root 1 plus 4 times zeta to the power of 4. So it's an interesting formula, and it is phi m. So I used, maybe I should get rid of this. So I used A tan D, this d is for degrees. You can also use A10 and then times 180 divided by pi, but you can also be lazy and do A10d. If you have a calculator, just be sure that you are using degrees. So let's see what the phi m value, the phase margin here, looks like. So phi m is 58.59. So what does this tell me? So this means that instead of using 180 degrees, negative 180 degrees, I should add 58 degrees to it in order to approximately get the zeta value that I'm looking for. And that's basically it. Now, there's no settling time, there's no rise time, peak time, etc. We're just interested in overshoot. And there are no dominant poles, nothing. Just the angle condition that is going to be updated, and that's basically it. So let me show you, let me demonstrate you. So since I know that this is phi m, the phase d, the desired phase value here, is basically minus 180 degrees plus phi m. And that's it. I'm just going to search for this point. So let me take this here. And paste it here. So we're looking for plus phi m. Therefore, I'm not going to look for this, I'm looking for phase d. The difference between phase d, this value, and phase should be minimal. Now we will find the frequency, the phase value in order to check, verify, the magnitude, k will be this, and we're basically done. This is the only step that is necessary here. So let's use red for some reason. So yeah. The frequency, everything will be documented here. So, it seems like adding 58 degrees gives us negative 121.66. And this happens at omega equals 2.45. The gain value is 80. And this would be then the closed loop that we have. And as you can see, the distance here is phi m, so the degree here is basically determined by phi m, so minus 180 plus this 58 degrees. And we're looking for this point. So once we have that point, we have a certain omega value. At that same omega value, we have a gain. We take the inverse, and that's the p-type controller that hopefully gives us the value. Now, of course, let's test this. Instead of looking for ZBK, what we might do is we might open up figure 2 and look for the step response. So let's display the data on the title. So overshoot and then plus step info ts comma overshoot point overshoot. That should be it. There we go. Let's run this. And we have another figure. Of course, maybe hold on would help us. There we go. Now, the overshoot value seems to be a little bit off because we were looking for 10%, but we got 26% here. Now, the reason for this is a bit complicated because Well, zeta is again a second order transfer function parameter, and we have a third order one. And also, we don't really care about the poles and zeros, but we know from the time domain design that it is important. It is important how the poles are placed. So let me maybe display the pole zero map here. Well, let's have a side-by-side thing. Let's have poles, zeros, PZ map, and then TS. Let's plot this. And then C zeros. Like that. And yeah, maybe I should also use an S grid here in order to have certain zeta values and omega n values. Let's have omega n up to 5. Let's get rid of this. Yeah, that should work. Let's see. Yeah, we forgot to update this here. There we go. So, let me maximize this. So we kind of chose the red dots here, or the squares. And the reason for that was basically the relation between zeta and overshoot, and the relation between zeta and the phase margin. Phase margin being the distance between this and this, namely 58 degrees. And yeah, it has a certain accuracy to it, and I can see that the zeta value is much less than it should be, because we should be on this line, but we're here somewhere. And the reason for that could be the effect of this pole, because zeta is a second order or a pole pair parameter, a second order transfer function parameter, but here we have a third order transfer function, therefore it might not work that well. What we can do, by the way, if we see this, we can just take this phi m value, and we could be okay with this, but the nice thing about the frequency domain is the following. The relation is not really important. If it's not that correct, we might correct it a little bit. I can see that the phi m value is not sufficient. I should increase this distance in order to have a better zeta value. Of course, I don't really know how much it should be, but I could try. I could maybe add 10-20 degrees to it and see how it works. Let's do that. So I might iterate a little bit. And you might ask yourself, why should we do this? If we can use the time domain method, and if we can directly calculate the best setup that is possible to achieve 10% overshoot, why should we use frequency? Well, we'll see. We'll see at the end, hopefully, of this lesson today. So, yeah, I calculated a certain phase value that should be ideally the overshoot that I'm looking for, but it didn't work, so let's add 20 degrees to it. And let's observe what happens. So again, this one and this one, and yeah, still not enough, but a bit better, seems like, because we're a bit closer to the zeta here, to the zeta line here. I should increase a little bit more. Let's add 40 degrees. Seems like the correction we have to correct too much. Yeah, we have 10% almost overshoot. I could add 2 degrees, maybe more. So something like this should work even better. There we go. We are almost on the line. Just maybe 1 more or 2 degrees more. This is really not that necessary, but yeah. Yeah, we could be happy with this. In fact, it's even too much. The previous value was better. So it's 0.25 or something. So yeah, not really that important. So this works. This is 10% overshoot. But we did actually go back a bit further to the left. But you can see that the poles start from the j omega axis and they go kind of like this. And I can therefore also see the fact that the zeta value is increasing if I decrease the frequency. Well, this is especially for this system. I cannot generally say that this is true, but you have to maybe observe the root locus and then maybe have an idea about that. But if you don't have any root locus, you can just do this. You can just decrease the phase margin a little bit or increase it a little bit to adjust to your wish. So yeah, what did we use as the phase margin here now? It seems like so there was phase D, so plus 180 degrees. So yeah, we have kind of used this value here. Phase D is 79, I guess. Yeah, we kind of have tweaked the value here. And yeah, let me see, phi m plus 42. That's basically the value that we are looking for. This should be basically the value that we should look for. So now the zeta value is 0.59, and sometimes in order to approximate the phase margin we can also use 100 times zeta. So adding 59 degrees would also be a good approximate here, whereas phi m on its own was 58 degrees. You can see that basically the complex formula here can be avoided in certain cases. You can see that instead of using this here, you might want to use 100 times zeta. But it has a certain accuracy to it. As far as I remember, for high zeta values, this 100 times zeta will be much different than the actual formula. But just to be a reminder, you might go ahead and use 100 times zeta if you don't remember the actual formula. But in our case, it's still not sufficient because it gives us 59 or 58 degrees, but where we need 42 more degrees to it, so we need to use 100 in order to obtain the actual overshoot value that we are looking for. So I will debate or talk about the debate of using this frequency method or using the time domain approach. We'll talk about that later. So yeah, basically A and B tell us the following. If we are looking for a stability interval, we are looking for a division by zero, which means that k times g omega should at some point be equal to -1. It could be that k is positive, therefore the argument should be satisfied by the system. The argument of the system should be negative 180 degrees. At that frequency, the gain can be inverted so that k times g omega is equal to 1. That will give us the k value for the p-type controller for the upper bound of the stability interval. It might also be the case where k is indeed negative, therefore the negative part is already taken out, so the argument should be equal to 0 because their sum would be minus 180 degrees. Therefore, for phase 0, the frequency, and then for that frequency you obtain the gain of the system. But this time you have to take into account that k is negative, therefore minus 1 divided by g omega at that frequency gives you basically the lower bound for the stability interval. In B, we have seen that with some errors, with some accuracy to it, we can basically use a certain phase margin, the margin from 180 degrees back to a certain value, and that value, or the distance, the phase margin, corresponds to basically zeta and therefore overshoot. If we have a certain distance, we will have a certain zeta value. Of course, the accuracy is debatable, but it is a third order system. We cannot really associate a zeta value for the overall system. We can only associate zeta to its second order part. Therefore, we have to work with it. But since we can tune our solution, we can start with the given phi m, and we can maybe adjust it a little bit and then end up in the solution. It still works, but the relation might be not that correct. So that's that. Let's see a different controller. Let's try to design a phase lag controller and to obtain a better response. And here we need to try to add a phase lag controller that will reduce the steady state error tenfold. Now we have seen that, let's see, we have seen that basically we have a certain steady state value. Here, in this case, we have this value here. It is 0.6289. What we want to do is we want to calculate the steady state error, and then we will reduce this by tenfold. So therefore, we will start with, let's say, design 2. We will start with the following. So first I can use this y here and the end value for YSS, steady state value. So y end is equal to this. So let me there we go. This is the exact value. And for this, I know that since I'm looking at the step response, 1 minus YSS would give me ESS. So this would be the steady state error. Now I want to reduce this by tenfold. So the new ESS should be ESS divided by 10. And therefore, I can again use this relation here in order to find the actual Y value. So, yeah, let's do that. 1 minus ESS gives me YSS. So let's see what YSS should be. YSS2, basically. So what was YSS? ESS2. Yeah. So ESS divided by 10, 1 minus YSS2 gives me ESS2. So this is YSS. There we go. Now, we have to get 0.9629 in this case in order to meet the requirements of steady state. So yeah, therefore we need to look for the steady state closed loop. We know that we have k times GSS and then divided by 1 plus k GSS. So that's no problem, we know that. And since k is static, what we can do is we can look for a certain p-type controller that will give us the required steady-state behavior. The problem would be the following. We don't really want to change the transients of this system. So if I indeed change the gain value, if I use the k value that I'm going to calculate in a moment, then the system might not be stable. So we'll see. So if I have this, and if I'm plugging in s equals 0, so if I'm looking for the final value theorem, s times that, or I can just directly look for the steady state value of GSS. So I can directly see that this is 1. If I plug in s equals 0, it is 1 divided by 24. Since I have k times GSS, this is basically k divided by 24, 1 plus k divided by 24. Or if I multiply with 24, I'll see that this is basically this closed loop gain. So this is not needed. There we go. Now this should be equal to YSS2. So that's basically it. Now 24 plus k times YSS2 should be equal to k. This would be YSS2 times 24 plus YSS2 times k equals k. So I want to work out what k is, therefore we'll have this. And therefore k would be YSS2 times 24 divided by 1 minus YSS2. If we didn't miss anything, we should get basically the value here. So if we have k equals 622.83 as a value, then we would get the steady state value that we're after. But as far as I remember, the value that we can reach is 351. Therefore, we need a dynamic part to the controller, the lag controller, that will basically compensate for this. Now, of course, keep also in mind that this gain is basically on top of the p-type controller that we designed. So, what was the controller that we've designed? Let's see. Well, we used, where is it? 40, yeah. So, the lag controller should have basically this gain. Therefore, you might think about the p-type controller. So lag times lag connected. Let's make that this lag connected to the p-type controller, connected to the system, and then the closed loop. You can maybe think of this. Then there's this feedback loop here that goes from here to here. So if you have such a connection, you might also get rid of p and just use lag. It depends on you. But we don't really want to change the p-type controller, and we want to design it on top of this. So therefore we need to use an overall gain of 622. So the gain of lag times gain of p times gain of system should give us the given steady state error value. So now, yeah, let's go ahead and include this gain, but as you can see, we will have basically a problem here. Now, I'm going to do the following. We have a certain gain value, so let's have that. And Yeah, well, basically we can skip this part and we can just use phi m. That if it's going to be necessary, we'll use that. Now, if we have k, if we want to design, let's say s plus z, if we want to design a lag controller, s plus z, and with the value k that we want to use here, so if the controller looks like this, and if we have the system here, there are two options that we could do. First of all, before those two options, we see that if we have the setup, then our controller s plus z, s plus p, if z and p will be chosen, then the gain will be k times z divided by p times gs. Now, we don't really want that, because we don't want to change the gain of the whole system, because we've already decided on the gain. We know what the overall gain should be. So this should be k. Therefore, we should maybe update our notation. Instead of having s plus z, maybe we should use s divided by z plus 1 and s divided by p plus 1. This notation has again s plus z divided by z, s plus p divided by p, and those divisions go here. So it changes basically the gain, it adjusts it back to k. But here you can see if we plug in s equals 0, you can see that this has gain 1, this has gain 1, 1 divided by 1, so we have k times GSS. And if k is equal to this value, 622 divided by 24, this would be the gain, and 25 point something divided by 1 plus 25.91 should give us exactly the value that corresponds to 10-fold reduction. So, yeah, we have kind of this notation here. Now, the upcoming part that I'm going to show you will be about this zero and pole choice, so that the system becomes stable and usable. But therefore there are two options. One is to use the body plot of GS, but then you have to compensate for K. Two, you can just include K into GS and draw a new body plot and use that in order to design your lag controller. So I'm just going to use a new body plot because it will be more clear to understand. So let me take this code here, bring it back here. Once I've decided on my gain, I'm going to apply this gain, and I'm trying to look for this. So I'm kind of going to decide on Z and P, but I will look at the body plot of K times GS. So now, well, the design of a lag controller is pretty straightforward. First of all, we want to have the same overshoot. Therefore, we will again use this one here. So let me maybe choose this here. So we still want to have that. Maybe here. But you can see that if I look for the argument of this, then I'll have this dynamic part. This will be j omega, and this will be j omega. And if I decompose it, it will result in the argument of this, and then maybe minus the argument of this, and then plus the argument of that, etc., etc. Plus the argument of this. The bad news about this is that I don't know what Z and P are. And I'm looking for Z and P. Therefore, I cannot really determine what phase angle I should get. But in the end result, I'll need minus 180 degrees plus phi m, so phase D basically. So I want to have this satisfied, but I only know, in our case, I can just look for this because I've updated my body plot. So I'm really interested in finding this here, but I need to get rid of Z and B because they are not determined yet. In order to solve this issue, and since we are looking for a lag controller, the contribution of the lag controller, if you think about the root locus, if you have a design point, the contribution should not be that huge so that the point does not change and is still on the root locus. So therefore we will make an assumption that this effect will not exceed 10 degrees. Therefore I'm going to plug in minus 10 degrees here, and therefore I'm going to be a bit safe and say instead of looking for phase D, I will look for phase D plus 10, and then the lag controller will have minus 10, so therefore we will have phase D. So this is an assumption and it might need an iteration, but it's better than nothing. So therefore, instead of this, I'm just going to add 10 to it. Let's get rid of this. And of course we need the point where this happens. By the way, let me also again update my controller. Instead of looking for s divided by, so let's say tau, s divided by z plus 1, we could just say tau, and then this is again tau, but alpha times tau. So yeah, it's a prettier way of defining the lag controller. Again, plug in s equals 0, you will get one gain, so the gain will not change. The gain is crucial because we want to have a certain steady state behavior. So we want to just add some phase to the system so that the system is stable, because for now using that p-type controller does not help because it's out of the stability interval. So I've added 10 degrees. I have to search for the point where this happens. So this would be the point. Let me also maybe look for this and maybe display also the value here. So we have phase D, which is calculated here. I'm looking for the phase value, but since I have updated my body plot, it's not a problem. I get omega val, phase val, mag val, k val. Now, of course, k val does not mean anything for us. First, we get the frequency. We know we need the frequency here, and we have calculated the frequency. Namely, it's omega val. Now I can also check phase val and mag val, but k val has no meaning for now. So the next thing is that in my controller I have tau and I have alpha, and I need to determine these. So tau is kind of the time constant. So, and since we can use omega times tau equals 10 or less than or equals 10, basically less than or equal to 10, because our assumption was 10 degrees, omega tau would be 10 degrees. You can check your notes. It's basically a step-by-step algorithm to calculate the phase lag controller. Now here, since we have omega val, I can choose a tau value. I'm basically choosing it. Now I'm going to choose it 10 divided by omega val. Now this is the way of obtaining tau. Once we've obtained tau, what we can do is we can look for alpha, and alpha is basically the gain value, so mag val. And you can use this tau and this alpha value and construct your phase lag controller, which I'm going to do. So instead of that, let's say alpha and also tau in order to see what these values are. There we go. So before I do anything, let's run it and see. Now we can see that here we have that, and then here we have that. Well, let me check if I No, it's not 2, 3, 4. 1, 2, 3, 4. 1, 2. Interesting. There's some duplication, I guess, but yeah. Let's add another space. So of course this is phase D. In our case, phase D is minus 69, so let's have 69 degrees. So somewhere I'm displaying it, but I'm not really seeing it, so yeah. Why do we have this and no spacing? I'm not really sure. Well, yeah, it's not really important. So now let's check if the lag controller works. So I'm going to use the K value that we had. Let me check here, K. So we have K. This is 622. So I'm just going to include that here. 0.83. Let's just use K times TF. That would be that's tau, that's 1, alpha times tau, and 1. And then we have GS, and then the closed loop. So feedback Fs times GS, comma 1. And that should be it. Now let's copy this portion here in order to see what really happens. So let's call this figure 3. Have step response, and maybe all the other stuff. So that was figure 1, figure 2. Something is messed up here. Yeah. Why do we have this interesting thing here? Let me check. So we have this, which is no harm. But then we have this. Whereas this should be AX1 and AX2, I guess. X1 or X2, X2. Here that should be X1. Of course, X1. Tile that. Oh, wait a minute, no. I somehow messed up stuff, but yeah. Let's close all the figures and check. And don't waste time. Yeah. So we have figure 1, but for some reason we are plotting some stuff that's not valid. Oh, is it this one? I guess it is. Yeah, that's that. Because we have updated our body plot, we are plotting again on the old one, but there's a big gain difference and that causes some issues. So let me just take this and call it the difference. So design 2, here we have that. So let's also create another figure. So this is 3 here, so that this is 4. Hope that this changes stuff. So now, this was the old setup. We've used these here, but then we have the new setup here, and our body plot is missing, of course. Let's also maybe add that. Yeah. We are plotting the body here, so therefore that should solve it. There we go. Now, you can see that there's a difference in the body plots. We have a very low gain, but here we have increased gain. But you can also see that using the lag controller, we have kind of increased the stability of the system, because it was not possible to use the gain value that we needed to use in order to decrease the steady state error tenfold. But yeah, we have kind of achieved that. But of course, it's also important to note that the behavior is not really as expected. So we have basically an interesting overshoot value. That's not really what we are after. So yeah, we have kind of our lag controller, and since again we have assumptions, like 10 degrees is the assumption here, so let's maybe check the body of our controller. So let's open up a figure for this. And see what we have here. And the frequency here was 1.22. So therefore we need to pick this. Here the frequency was 1. What is it now? 22. So somewhere around here. And we can see that there's no 10 degrees of effect. Therefore we have a bit of an issue. Maybe we can get away with a lower value. So let's try that. We have used, so you can basically change this here and also this assumption here. So let's have 6 and 6. Let's try that out. Did it increase the performance? Well, it's not really that affecting now, because yeah, we've kind of moved the poles and zeros a little bit, but we didn't get what we were looking for. Maybe we should just look for figure 5, and again body of fs. And 1.22 again. We have 1.25, 24. Now we have 8 degrees of face angle, so we might also choose 8. But yeah, it's not really possible to increase the performance of this. Seems like it. But yeah, what we can do is we can go back to our original system here and maybe give it some room in terms of, let's find that place. In terms of this phi value, I want to check out what happens if I get rid of this adjustment that we've done here. That was 42 degrees. So let's start with a worse p-type controller and then try to adjust our thing here. So this would mean that, let's change it back here. This would mean that here down here somewhere, we use that phase D value. There we go. So what we can do is we can get rid of this effect here maybe, because we are adding extra poles and zeros. What happens if we change it like that? So let's see. Yep, it works a little bit better. Again, it's a little bit off, but we have a better overshoot. So the thing that I did was I adjusted the overshoot value, but since I have an assumption there, I'm just changing, deviating from the original formula. And on top of that, we have the assumption that the controller has some angle contribution. We went far to left on the body plot. Therefore, the zeta value become 1, and we didn't have the overshoot that we wanted to have. But if we change it back to the original value, even though the p-type controller is not really at that point where we're looking at, you can see that 10% overshoot can be satisfied with that adjustment. I have seen that we added too much phase margin, so we just left that out for this. So you can see now, at this point, it seems to be a good approximation for 4 poles and 1 zero. This approximation works for some reason, but for 3 poles it doesn't. So there's a little gap there. You might adjust sometimes, and sometimes it's too much, sometimes it's too less, so you have to kind of compensate for that. Now you can see that it has a better shape and a better overshoot value. Of course, I need to adjust a little bit more, so I could go ahead and maybe add 5 degrees to so yeah, this time we messed up the overshoot value again. So yeah, you have to iterate a little bit. You might ask yourself, so yeah, how can I know if I should add it, if I should not add it? Well, basically, if you're in an exam, you should not add anything. So just follow the instructions, follow the algorithm, and that's it. Don't adjust too much like I did, for example. And you should be good to go. Now, here in the frequency domain, the design of a lag controller is pretty straightforward. Let me recap. For this question, we had the steady state requirement to reduce the steady state error by tenfold. Therefore, we had to come up with a gain value that would end up in doing that. But the gain value on its own would not work because the stability, it is out of the stability interval. So there's no p-type controller that satisfies that. But we might be lucky with a p-type controller times lag, or directly the lag controller. So we have chosen the gain of the lag controller, and then we have adapted the lag controller definition so that we have tau and alpha, which don't affect the gain, the overall gain. And here we looked for the same phase margin, but we added a little bit, 10 degrees, 5 degrees, something between that, because the phase lag controller will have an angle contribution of 5 to 10 degrees. Then we used basically again the data that is obtained from the body plot. We took the frequency, the phase value, the magnitude value. Of course, the phase value does not make that much sense, but in order to verify it. And then we just used the fact that omega times tau is less than or equal to 10. If you added 6, you can divide 6 into omega val. If you added 10, which you should do, divide 10 by omega val and you will get a tau value. And the exact magnitude value at that point is basically the alpha value that you look for. And when you have tau and alpha, you're basically done. Plug it in, define your controller, check if the closed loop works, and you're good to go. For the p-type controller, this is much easier. You don't have to really look for the angle contribution of your controller because your controller is static. But in this case, you have an angle contribution, and you should check that out. So, our final thing of today is the delayed system, a system with delay. So let's focus on that. Now, it is interesting and important to note that, well, GS is equal to this given second order transfer function times a certain amount of delay, like 2 seconds. But it is important to note that this does not change anything about our analysis, synthesis in the frequency domain. Because if you can plot a body plot of a system, all the rules apply. So let me show you. Since 12, 1, 10, 24. 12, 1, 10, 24. Since this is a basic system, we have IO delay of 2 seconds, I guess. And let me just copy this part of code here. Yep. Now let's call it 5. And let's get rid of k. And that's it. So if I want to look at the body plot, this is the code. Figure 5. And we're basically done. We have our body plot. So at this point, we can use this body plot to design controllers, to come up with a p-type controller, to do whatever we want. So that's basically very powerful. So in terms of the question that you might ask yourself, why would I use the overshoot value, the overshoot zeta phase margin relation? Well, the answer would be the following. If you have a model that's hard to work with, for example, a high order transfer function could be the case, a system with delay would be the case, or any other system that can have a body plot, you're okay to use the frequency domain approaches because they don't really care about the poles and zeros, but the accuracy is also not really that good. You have to compensate on your own. You have to affect your solution a little bit. You have to adjust stuff, tune stuff. But the basic algorithm applies, and you can just design your controller or make your analysis. On the other hand, if you're interested in precision, in control, and you're okay to model stuff, you're okay to work with polynomials, and you have no delay, etc., etc., or you're using a Smith predictor, intermodal control, whatever, then you should stick with the time domain approaches, because those are aimed to precision to a certain degree. But the frequency method does not really use the model itself too much. It uses the frequency response of the model. Therefore, it's an indirect design method and analysis tool. Therefore, you should use that for those. So, for example, if you have a system with delay, if you don't want to use putty approximation because it's a bit difficult, if you're just interested in a p-type controller, lag controller, lead controller, just basic stuff, then just use the body plot. If you can obtain that, just use that. Because it's indirect, therefore it doesn't care about the amount of delay. You can just go ahead and use all the steps that you use for any body plot. So this is the power of the frequency methods, because it uses the body plot. It utilizes the body plot. Of course, there are also Nyquist plots and also other plots based on the frequency, but body is the most important one because, well, basically -1 is an important thing. You look for 180 degrees and gain 1. In Nyquist, you again look for -1 because of the same reasons. So yeah. If you know body plot, you would be able to, you should be able to just use other frequency-based plots. So yeah, what we can do is we can just go ahead and take this part here, this analysis part, look for the angle condition, take that, give the info. Let me just paste it here. So we're basically looking for the phase angle, negative 180 degrees. We look for the frequency, take the frequency, look for the magnitude, take the inverse, and that's basically it. Yeah, let's try this out. So we have figure 5. We can see that this frequency was the frequency that we were interested in, and we have 2.15 as the gain value. So again, this is just a direct method. So when we were using the Putty approximation, I told you that using the Putty approximation gives you basically the interval of instability, not the stability, because it doesn't guarantee you. This is an approximation. The higher the order of the approximation, the higher the accuracy, but it does not guarantee you that if the approximation is stable, the system is stable. That's not guaranteed. But if the approximation is not stable, then the system is definitely not stable for the Putty approximation. Here in this case, if you are using the body plot, that's not that big of a deal, because you're directly looking at frequency domain response, and this system has this angle value at this frequency and has this gain. Therefore, you can use this p-type controller and it will end up in marginal stability. So it's a more direct thing. So the problem with systems with delay is basically the fact that we cannot use pole zero map on it. We use pole zero map on it, but it gives us the minimum phase part, so the poles and zeros, not the delay part. It excludes that in MATLAB. But we are not able to plot the root locus. We don't have any polynomial in the closed loop. That's a big issue in the time domain design. But here we can just plot the phase plot, and we can just use all the frequency domain methods that are available to us. So that's important and powerful. For delay systems, you might want to check this out. You might want to look for the body design methods. For some high order systems or systems that are tough to deal with, you might also check out the frequency methods. But the frequency methods do not guarantee precision. You have to work a little bit with them if you want to have some precision. So that's basically that. And let me also note that here the phase angles got a little bit out of control, and I can explain you the reason why. So let us check out the PDF, because it's a bit more helpful. Now this is the body plot, and this was basically a stability analysis question, namely A. We have obtained the point where, or we looked for the point for minus 180 degrees, the frequency, use that frequency, obtain the gain, take the inverse, gives you the upper bound. You can also find the lower bound, and here is also the basically symbolic solution, or the exact solution. I did plug in S equals j omega, and then I kind of changed the notation here around a little bit. This is basically the gain part, this is the phase part. I'm looking for e to the power of minus j 180 degrees in phasor form. So therefore I need to look for the argument of this. You can use a tan here. So this is minus arc of this complex number, and then use a tan, imaginary part divided by real part, and you'll get omega 5.84. And plugging in this as j omega, so j 5.84, into the transfer function, you can do that. Plug it in here, or choose omega to be 5.84 1024 and use this expression, you'll end up into 0.0028. Take the inverse and you end up in the upper bound. Now this is not correct. We should check out the negative part here. And I left it out for some reason. Yeah, but this is not correct. I've shown you that the negative part is 24. For some reason I might have missed it here, but please correct this. It is in the video at least. So here's the code, and then we were asked to design a controller, a p-type controller that will result in 10% overshoot. We've calculated the zeta value, then phi m, the phase margin, is then calculated with this relation, and we have 58.59. Or you can take 100 times zeta, which is 59.12, which is approximately the same. It is also an approximation that works, but for high zeta values, this might be not that big of good of an idea, because the phase margin becomes 100, but it's not really 100 according to this relation, etc., etc. Yeah, because this decreases if zeta increases, definitely. So yeah. Then we looked for the phase margin that is necessary, 58 degrees. Add this to negative 180 degrees, and you will end up in this value. Where does this happen? At which frequency does this happen? Therefore, the gain at that frequency gives us the p-type controller that we are looking for. Then we had a steady state error value. We needed to reduce it tenfold, so we worked our way out in order to get this gain value, because this has a much lower steady state error. So therefore we have 1024 here. Numerical differences are for the fact that I have adjusted the value here. We didn't use 121, we added 42 degrees to this, so yeah. Then you add 10 degrees because tau s plus 1, the zero of this, alpha tau s plus 1, the pole of this, they will contribute approximately negative 10 degrees, and if I add 10 degrees, it will again end up in the same point. So therefore, we add 10 degrees, search for this point, and this point happens for omega equals 2.1. At this point, we calculate the tau value by using this relation here. 10 divided by omega can be chosen as tau. If you choose this tau and choose this alpha, you'll get the controller that is shown here. You can see that 0.21, it's close to the origin. This is even closer to the origin, and you can see that the pole is here, the zero is here, so it's a phase lag controller. And then we can also see the comparison here. We have the p-type controller, but then we have the lag controller. We have kind of the same thing here, but we didn't promise that we will have the same settling time or the bandwidth. Therefore, the response did change a little bit in terms of settling time, but yeah, we don't have any settling time here. So then we can see the effect of the lag controller, phase lag controller, and the p-type controller. You can see that it has a negative angle contribution, whereas the gain is increased a little bit, and then for some higher frequencies we again have the same behavior, because this is our domain where we affect the system. So we're basically aiming the step response frequency and the low frequency values, and it doesn't change in the other frequencies, so it's also nice to see. So here we have a transfer function with a delay, and this is basically the body plot of that. And in order to look for the stability interval, what we can do is we can just use the same rules here, 180 degrees, look for the frequency, at that frequency take the inverse of the gain, and you will end up in the upper bound of that. You might also want to check out what the negative one is. I'm not sure if this is 0 because there was an error previously, so this might be also not really true. So we can see that at this gain value we have basically very low zeta value, so somewhere around the j omega axis. Now here, an interesting fact is that we have the minimum phase part, which is basically the transfer function 12 divided by s squared plus 10s plus 24. And if we plot the body plot, we see that the gain plot is not affected by the delay part, e to the power of minus 2s. It doesn't really affect the system because it has gain 1. If you plug in j omega, you will see that e to the power of minus 2 j omega affects only the phase angle. And since there's an omega in it, it affects really, really much. You can see that it basically gets out of control. Therefore, adding delay to a system for a closed loop design, you can see that the stability decreases of such a system. So that's also nice to see. And the effect here is exactly omega tau. So in this case, it is 2 omega. If you take minus 2 omega, if you add minus 2 omega to the original phase, you will get this blue plot here. Since omega gets out of control, the phase gets out of control. So that's also important to note. Now, of course, there's a phase lead controller design, but I didn't include it because it would have been too long. It's already too long. So therefore, that might be in another, maybe in the question solving session for the final exam. But for now, this is basically the frequency domain. We've talked about stability, we've talked about the phase margin and its relation to overshoot. Therefore, we've seen that we can also use this for synthesis. And we looked at a delayed system, the system with delay, and we've seen certain stuff about this. We've seen that we can design a controller, we can analyze this system, and there's an important difference here, that this affects directly the phase, but it does not affect the gain. Now, in the exams, I will probably talk about this later, but remember that we basically used k times gs for the body plot somewhere here. That might not be the case in the exam. You might want to take into consideration of the effect of the gain on your own or manually. If we have gs, if you read something out of that, you have to multiply it with k in this case for C. It's a good idea to try it out maybe. And here it is also possible that in the question the delay part is not included into the body plot, so your body plot would look like, could look like, let me find it, could look like this reddish color here, and you might have to subtract tau times omega on your own manually. So those are important to note. Sometimes such questions arise, so be prepared for that. So that's it. Hope that this was helpful, and I see you in the next lecture.